As part of our electricity, we're going to continue with it. We're going to introduce the concept of internal resistance. We're going to talk about it. We're going to do a couple of examples on it, right? Well, what is internal resistance all about? You know that when you see a battery, they tell you certain things about it. Generally speaking, I'm just going to put a heading here. Internal resistance. Okay. Now, inside the battery itself, what is happening? If we go back a bit, we had chemical energy changing to electrical energy. Incidentally, we've really got a redox reaction inside there, okay, going on, where electrons are being supplied and they are flowing around. They go around the circuit, we assume from positive to negative, the conventional current, and what do we say? We say they go around. But when they get back to the battery, they're tired. After all, what have you done to them? You've squished them through resistors, okay? You've stuck them in capacitor plates, all right? You've accelerated them, you've slowed them down. You've made them rub up against each other and give off heat. I tell you, being an electron is not an easy business. But now, what have we done? These electrons have lost, they're tired. They get back to the battery, and what do? We recharge them. We give them a pep talk, I don't know, give them an energy drink or whatever, and we send them back out again, don't we? That's what we do. Okay, so we're kind of cruel. We're continuously charging up electrons and sending them out because the electron is our measure of current, isn't it? How many electrons flow? So that is why inside the battery, there's also an internal resistance. Remember when you've had a battery's been working for a while and you touch it, it's warm. That's heat being lost by the internal resistance of a battery itself. Now, how do they look at this? We've got this. Let's just look at a few concepts first, right? Let's just look at a concept. Over here, okay, we've got our circuit and we've got our group of cells over here, right? Like that. However many are in there, it doesn't matter. And what happens in the circuit doesn't really matter. Now, when we place a voltmeter over here, all right, like so, and the switch is open, we know that there's no current flowing in the circuit, all right? Forget what happens in the circuit. That's a short circuit, so let's put an R in over there. Okay. There's no current flowing. That voltmeter reads what we call the EMF, and we've been through that before. The electromotive force, it reads EMF. We give that a symbol, and we call it little or big E like that, epsilon. I think it is the Greek one. That's what we call it. Now, what is the next thing that we do? We say, all right, that is what we read on the battery. Let's have a look at the battery. What does a battery look like? Battery looks like this. Like that, right? And on the side, it tells us 12 volts or whatever it is, right? This here that they put is actually the EMF. That is the maximum voltage that you can get across the two terminals, all right? It's kind of pretty much the voltage of the source, okay, V source. It's the voltage of the driver of the electrons, because that's what it is. We're driving electrons around and around, aren't we? So that's the V source. Some textbooks do that, okay? But for our purposes, let's call it EMF, maximum voltage. Okay. Now, what happens when we connect a circuit up? I'll tell you what happens. If you've got a voltmeter on the battery, okay, across the battery, you actually suddenly don't read that. You read V load. That V load is the voltage that drops. The battery drops its voltage. This over here is V internal resistance, Some textbooks call it V lost, lost volts, okay? It's not lost, all right? It's just a conversion. Don't think it's disappeared anywhere. The terminology, yeah, whatever. But the point is it's not lost. It's not gone, all right? You can see here that the total V EMF, okay, sorry, I mustn't write V EMF. That was my bad. The EMF is equal to V load plus V internal resistance, right? So what happens is when you flick the switch, there starts to flow. So it gets a V of the load, which is the circuit load. It's also called the external voltage, which I don't like either, but it's not for me to say. But I kind of prefer to think of it like this, that it's the load when it's being pulled around by the switch closed. So therefore we end up with a formula. What is V load? It's IR, isn't it? What is V internal resistance? It's I, and we call it little r is the internal resistance, which is equal to I times R plus little r, which is the formula that you're going to see. Okay? Working it backwards, it's saying that the current in the circuit, because the current must go through the whole circuit, let's track it. Remember what we said in circuits from last year? We said put in the current. There we go. I. And when it's running, I must go through the battery as well. Right? And the battery's got a resistance of R. So there's going to be a voltage drop across the battery. So that's the voltage drop across the battery over there. Okay? VIR is going to be, let's call it the voltage drop across the battery. All right? That's, in other words, it's the same as the voltage drop you get across a resistor, isn't it? Remember, resistors, you get a voltage drop when the current goes through it. Righty-ho. Now we've got the formula that we're all going to see and that we're going to use, etc. How do you see this? Well, either, number one, they tell you R is equal to 2 ohms or whatever it is, or number two, they give you a battery like this, like so, and they give you, okay, and they tell you that the battery EMF is 12 volts and it's got an internal resistance. This little resistor is the internal resistance. What they've done is they've split it, the battery with its own little internal resistance, and put like a little dotted line thingy around it, okay? Or they could just say to you, the EMF is equal to 15 volts and R, okay? So basically, this is the way they are going to give these kind of problems to us. Well, let's the only way to do this, and we can talk about it for hours, but let's do an example. That's by far the best way to tackle them. Come on, there we go. Let's do an example of this, shall we? Let's take this one here, right? We've got a circuit. I'm going to draw the circuit first, all right? Let me just draw the circuit. You can draw it with me, okay? I hope I'm not going against that too much, against the microphone. All right, let's just put in a simple circuit over here, shall we? And we say that, and they've given us that is their R, and then we come from the circuit down this side, and over here we're going to split into two. All right, split into two resistors, and I think they're given, they are 40 ohms and 60 ohms, like so. And then we continue down. And up here, they've given us a resistor Z, like so. All right. They haven't put in the dotted lines. And there's an ammeter over here. All right. And they say that is 0.5 amps. They tell us across here, okay, voltmeter. And they tell us that's 3 volts across there. And they say the EMF of this cell is 18 volts. Okie dokie. It's 18 volts. And let's see what we've got. Right. So we've got that. Okay. Now, never mind what they ask you to do. Sometimes the order that they give it to you is the logical way, but it doesn't matter in essence, all right? What I'm doing is I'm just going to go through and solve for what's missing in the circuit. Okay, that's what I'm going to do. What's the first thing you do? Yes, put in the current from positive to negative, I. Let us split up the current and say this is I1 and this is I2 over here. Therefore, that becomes I again, and I follow it round and I put I in where I see every component. In other words, in your case, where you see a resistor, okay? We don't do coils. In A-levels, we do coils and we do capacitors and things. We don't do it yet, which is great. Okay. So wherever we've got a component like a light bulb, which is essentially a resistor, isn't it? We put it in. Now, the next step is I say, okay, let's look for where I've been given what. What can I work out? Well, here we've got two resistors, okay? Therefore, can I calculate effective resistance of the circuit? Let's have a look. Remember, I put in my ghost resistor there, all right? And let's go and calculate it. Okay, let's go. First of all, I have to say what? I have to say that the effective resistance is equal to 1 over R parallel is equal to 1 over R1 plus 1 over R2 because they're parallels. Therefore, 1 over R parallel is going to be 1 over 40 plus 1 over 60, which is going to be equal to, and basically you'd use your calculator for that, and you end up 1 over 24. Therefore, the R of the parallel is 24 ohms, right? What do I do with that? I always go and I put it back. In physics, you put them back onto the drawing because you're going to need them. Believe me, it works. 24 ohms. I've solved that. Okie dokie. Now, next, let's have a look. Staying by this component, that's that. What can I say? Now remember, that's now I going through there, isn't it? Because I've cut the two resistors out and replaced it with one. Correct? So what do I say? I say that is the full current. Do I know it? Yes, I do. Look at this. We know that current. Therefore, I can work out V over there, can't I? How do I do that? Well, I say, hang on, I only know V is equal to IR. I'm now looking at the 24 ohm resistor. Can you see I'm just compartmentalizing it? V is equal to IR. Do I know I? 0.5, 24. So that's going to be equal to 12 volts. I then go back and I put onto my diagram, I know you're bored with me saying it, I put in 12 volts. Because that's a trigger, okay? It tells me, it says, wait a bit. Therefore, my V load, my V circuit, my V external loop, however the thingy's done it, can you see it, is 15, isn't it? 12 volts over here, 12 volts here, and 3 volts there. All right? I could have not been given that, but then I'd have had to have been given the value of Z. Well, let's calculate the value of Z. So I go back, let's just put it back to that. So resistor Z. V equals IR. That's all we have to remember, and you're given it. Voltage there was, hang on, it said 3 is equal to 0.5 times R. Therefore, R of Z is going to be 3 divided by 0.5 is going to be 6 ohms. Okay? 6 ohms. So I go back, let me fill you in, keep it as blue, and I say you are 6 ohms. Okay. Now, let's say, I don't know, let's say I do something else funny now and I say, all right, therefore what is V of the circuit? Circuit resistance in other words, total, which is R. R is going to be equal to 6 plus 24, which is going to be 30 ohms, isn't it? Therefore, V is going to be equal to IR, which is going to be 0.5 times 30, which is 15 volts, which is what we've worked out before. Okay? I'm just showing you different ways you can do it. Let us now go back and say, okay, what is I1 and I2 then? Okay, what are I1 and I2? Well, how do we work that out? What do I know? It's a parallel pair. What does that mean? A parallel pair means what exactly? It's a current splitter. So at the parallel pair, okay, they are current splitter. Therefore, voltage is the same. So the voltage across, I'm just redrawing it here so I don't have to keep going backwards and forwards, across the 40 and the 60 ohm is the same. What is it? And the voltage is going to be 12 volts, is what we worked out before. Therefore, I1, well, hang on, let's not get ahead of ourselves. V across the 40 is going to be I1 times 40. V is 12 over 40 is equal to I1 is 12 over 40 is 0.3. Sorry, that is I1 is equal to 0.3. Okay, and V on the 60. Okay, whoops, I've run out of paper. Okay, V on the 60 is equal to I2 times 60, and that's going to be equal to 12 over 60 is equal to I2, and that's going to be 0.2 amps. So let's go back and put it in red, just in case we need it. I don't think we do. So it's 0.2, okay, there is equal to 0.2. This is equal to 0.3, and the total is 0.5. So far so good. We are cool. But hold on, what's happening here now? Okay, we've got Z is 6, but what about we haven't done the other bits? Hey, we haven't done this R. So let's go and have a look at R. Okay, what are we going to do about him? Well, let's see, what do we know? Let's go back to the black. We know that, let's look at battery. Shall we? Let's look at the battery. EMF is equal to I times R plus little r. I was 0.5. R for the circuit is going to be, okay, 24 plus 6 plus little r. So therefore I'm going to have half of 30 is going to be 115, and EMF is 18. So 18 is equal to that, 15 plus 0.5 R, okay, therefore R is equal to 6. Okay, R is equal to 6 ohms. There we go. So essentially, what are we saying is we're saying that the battery, okay, read this. Just to recontextualize it, we said that the battery EMF was, 18 volts, right? I wasn't used to an 18 volt battery. Okay, EMF is 18 volts. This is V voltage drop due to internal resistance. This here is V load is 15 volts. This is my circuit voltage. Okay, it's, in other words, it's what would a voltmeter read when it's closed. a voltmeter across the battery, if we put a voltmeter across the battery, okay, let's do it in green. If I had a V over there, and we have a switch here, let's say, with the switch open, okay, so let's say switch open, V equals 18 volts. And switch closed, V equals 15 volts, which is the sum of those two. That's, in other words, the voltage under load of the circuit. Okay. Right, let's have a look at another, let's have a look at another example. Okay, this example is, you draw the circuit with me and we solve it together, because that's how this works, isn't it? Okay, it doesn't work you watching me. Okay, although that's probably pretty cool to do. No, I'm just joking. That's quite... Okay, and here they've given us 3 bulbs. All right? And I do know that my drawings are not great and not neat, etc. But remember, I'm trying to do this in a time constraint so that you get the maximum value out of it, because you can redo this afterwards, okay? So they tell us that these 3 bulbs are here with a 6 ohm thingy, and they say that the rating of the bulb is 1.5 watts. Okay, the rating is 1.5 watts. Okay, whoa, okay. Let's just first go back to basics. What do we do? I haven't asked a question yet, but, sorry, one thing I haven't put in, let me fill it in. The EMF equals 12 volts and R is equal to 1 ohm. Cool. Now, you're going to do an experiment with the internal resistance. If I've got time, I'll try and cover that one as well. All right, or we'll put in the extra ones. Okay. So what do? I go and first of all, I put in my current. Here we go, and I label it I. Over here, I comes, and it splits I1, I2, I3, splits to I, and put I through my ammeter over there. Okie dokes. What do I have here? Well, and I've got something that they've put in here, and they've called point X, and we'll get to that. Okay, here we go. Well, what can I say? Well, first of all, in this case, those resistances are equal. What does that mean with I? It means I1 equals I2 equals I3. Because it's equal resistance on all sides. So it's going to go through equally, correct? Then I say that also power is equal to I squared R VI or V squared over R. Right? So now let us just have a look and see what can we do with this. Let's do some calculations. Well, I'm given all the resistance first. So what do? I always look for most information. Most information is there. So I say for resistors in parallel, just so I know where I am, 1 over R parallel is 1 over 6 plus 1 over 6 plus 1 over 6. And that comes out to be 3 over 6, which is, well, do you want to do it? It's going to be 3 over 6, isn't it? Which is going to be a half. Therefore, R parallel is going to be equal to 2. Remember, invert. Okay? Common mistake that we make, we forget to invert. So I can now go back and I can put in the ghost resistor and I can say, aha, I was going to put it in over here. There she is. And that's 2 ohms. Right. Now, what did we say? Let's look for more info. We know the R over here. Let's put it in. Maybe that's a good idea, guys. Okay? If they give it to you like that, put this in and show it as 1 ohm. Just to remind you, there's now another resistor in the circuit. So therefore, what can we do? The next one, I can say R circuit is equal to 2 plus 3. Right? The total circuit resistance is that. Well, next I'm given an EMF. So I say EMF is going to be equal to I times R plus little r. Hang on, I know that, and I know that EMF is 12 is equal to R plus little r is going to be equal to 2 plus 1, which is 3. Therefore, I is going to be 4 amps. So I go back to my circuit and I put in the 4 amps. Let me change to red and go back to the circuit. And let's put in 4 amps, shall we? All right, here we go. 4. I don't know the split yet, and that's equal to 4, and that's equal to 4 amps. Well, let's see. Current splitter, but wait, hang on, I know my ghost resistor. Therefore, what can I do? I can work out V here. Let me just do this in a different, let's do it in blue, right? I can work out V over there. I've got the R and I've got the I. Okay. So therefore, let's say, what am I going to do? Let's look at V across parallel. Look how I spelled across. V across parallel is V equals I R. I is 4 times R was 2. I think. Let me go back and check. Yes, there it is. It's my, can you see? There it is. It's my 2. So I go back and I say that is going to be equal to 8 volts. Then I go back, and I do apologize for swinging the screen up and down like this. But I go back and I now put in my 8 volts. 8 volts there. And now I can go to each one. Therefore, let's work out the current through the bulbs. All right. Oops. Okay, getting a bit too many colors. Currents I1, I2, I3 is going to be V equals IR again, isn't it? V is 8 is equal to I times, and R was given as 6, wasn't it? So therefore I is going to be 8 over 6. Okay, correct? All right, what is that? 8 over 6. Okay. To be 8 over 6. Oh, well, that's 4 over 3. Right, 4 over 3 amps. Now let's go back to our circuit, and let's put in I is equal to 4 over 3. Okay. It's equal to 4 over 3. Now, the next question says, let me say what we're going to do. Here we go. We are going to put in a resistor at X. Okay. What value of R, okay, such that the maximize power of bulbs. Power equals 1.5 is going to be equal to I squared R, correct? But R is going to be 6, isn't it? Okay, so that's going to be, therefore, I squared is going to be equal to 1.5 over 6, because each one is 6. We're working out now using the power. So therefore, the current is going to be equal to 0.5 amps. We've got to reduce the current, okay? Because that rated value is to order to operate only 1.5 amps, okay? We're putting too much through it at the moment. So what do I have to do? Therefore, what have they said to me? They have said, okay, therefore, maximum I in the circuit is going to be equal to 1.5 amps. Why? 3 times 0.5, because 0.5 is going through each bulb. Therefore, the maximum is going to be 1.5 amps. All right. Therefore, in the circuit, okay, what do we know? We know I, we know EMF. 12 is going to be equal to, let's have a look, I is 1.5 times R plus little r. Little r is known. 1.5 times r plus little r. R is 1. Sorry, my bad there. Let me just delete you. No, it's the eraser I'm looking for. R plus 1. So 12 is going to be equal to 1.5 R plus 1.5. Therefore, okay, we come out with R for the circuit as 5 ohms. Okay? Cool. Now, if R is equal to 5 ohms, okay, then we've got to answer the question. R is 5, okay? That's the external resistance. This is the circuit resistance equals 5, isn't it? Well, what were the bulbs on their own? Okay, the bulbs had an effective resistance. Okay, the bulb's resistance on their own was, let me just see, bulb's resistance was 2. Okay, bulbs equals 2 ohms. Therefore, the resistance at X, I'm still on the last one, the resistance at X, all right, at X, okay, that's a bit irritating, isn't it? The resistance at X is got to be equal to, well, the circuit is 5 minus 2, which is going to be equal to 3. Okay. Well, because I need it to be there. Okay, let me just see. Right, circuit resistance with those. There we go. All right. So, 2, 3, yes. Okay. So we got our total circuit resistance is going to be 8. Correct? 3, 5, 6. All right. Sorry. Let me just go back here. Silly me. I've done that again. Okay. Let's just have a look. We need to have a total circuit resistance of, let me just check myself, is 12 minus 1.5. 12 minus 1.5 equals that. Divide by 1.5. It's going to be equal to 7. Sorry, my error. Sorry, guys. That's still correct. No, that's fine. Okay. Resistance is 7. Okay. This R here is going to be, therefore R is equal to 7 ohms. I did the division there incorrectly. I was just doing it in my head. I didn't look at my sheet. Okay. So what have I got? So the circuit resistance is 7. Okay. The total is 8, but I've already accounted for him there, haven't I? You see? The 1 is there already. So the circuit, the bulbs are 2. Therefore, the resistance at X must be equal to 7 minus 2, which is 5 ohms. All right? And you can check yourself back if you want to. Just put a 5 there and work out what your new is. Right? That's when we are looking at those. Okay? Hopefully that's been sorted. And as I say, in the exam prep ones, test preps, we're going to put more and more in as the site gets bigger, and we're going to get additions stuck into it. Okay, thank you for watching that. I hope that you can go through these internal resistance. Really, it's just a case of following the recipe that we laid out earlier and accepting the fact we've now got one extra resistor in the circuit, which is in the battery itself. Cheers. Have a great one. Bye.